Hi, you two.
Hello.
So Faith, you had a question on which homework problem?
73 is the last one that we have to do. It was just on the acetals. I was 14. It was for 16. It's for 16. But I guess I was just still kind of, I don't know. I thought I would get the acetals and then I didn't get the
Which number?
73.
Okay.
I guess I just didn't really understand how we do those. Because yesterday, or not
Oh,
yesterday.
crap. This is edition. I've given away all my third editions to be nice.
It's
So
okay,
we
I
got to
did
look at
fourth
the, what's that?
edition. It said it's okay. I did the same thing for fourth edition. Anyways,
Hold on. I can bring it up. I just need a second. So remember everybody, because I've been grading homeworks and then sometimes I don't understand what problems you're doing because you're doing a different edition. If you have a different edition than third edition, please do third edition homework problems so that we can standardize. And you're asking, how can I do that when I don't have the third edition of the textbook? I have been nice enough to, on those assignments. Why? See, this wretched computer. All right. I've given you a PDF of each chapter's homework pages for the third edition so that we're all using the same edition when we do our homework problems. All right, and which number was that? 73. Okay.
it was pretty much all of them, because as soon as I saw the acetals, I was like, shoot.
Okay. So we'll make it a little bigger so it's easier to see. What acetal is formed when each of these aldehydes or ketones is treated with two equivalents. So in other words, two of these methanols for every one of those aldehydes or ketones in the presence of H2SO4, which is an acid. All right. So remember, generally speaking, I'll try to color code this. And I'm showing a ketone here for an example, but it could be an aldehyde as well. Whenever we treat an aldehyde or a ketone with an alcohol in the presence of an acid catalyst, we end up exchanging both of those carbon-oxygen bonds for new carbon-oxygen bonds between this carbon and the oxygen of that alcohol. So we make an acetal. And that would look like, in a general case at least, this. So two of those alcohols end up attached at that carbon where the carbonyl group was. All right.
Okay.
Now, let's draw the same thing here. In each of our cases for this problem, the alcohol that we're using is methanol, a one carbon alcohol. All right. So our first ketone looks like this. Treating with methanol and an acid catalyst, we would expect two of these methanols to take the place of the two bonds to that oxygen. All right, and let's try and be grown-ups and not use color coding this time. That's a CH3 right there. I'm just drawing it as a bond line drawing. Faith, does that help?
Yeah, I feel like I get it. There was just a problem that we did on like for the actual lecture. And I guess for that one, I was just confused because for this one, for the example that you used, it kind of branched off even more. like it was this one, and then I didn't understand why it branched off even more.
Because of the different alcohol.
Oh, okay.
So that 3-carbon alcohol, there are 2 of those that end up bound to that.
Oh, okay.
Does that make sense?
Yeah.
So B is a little bit harder because this is the smallest aldehyde that we could possibly get. So I've drawn the aldehyde from B for problem number 73. If we treat that with methanol and H2SO4, now note that you might see the reaction looking like this and have to realize that because it's an aldehyde or a ketone, you're going to use 2 of these. It might not tell you.
Yeah.
All right. Now, this is kind of a tough one. Because that carbon right there is this carbon. All right. Note that there were 2 hydrogens bound to that carbon at the beginning. There's still 2 hydrogens bound to that carbon at the end. All right. This one is a little tougher to see as an acetal. But anytime we have something that looks like an ether 2 times over, in other words, 2 oxygens with carbon-based groups bound to the same carbon in the middle, that's an acetal. All right, that's just a nicely disguised acetal because there's not too much other stuff around it. Okay, any other homework questions to talk about before we move on? I've been trying to catch up all of you guys' homework grading. I haven't finished everybody's chapter 14 homeworks yet. I'll do those as soon as I'm done with class today so that you can have them to look over with my comments before you
Do
come.
we have chapter 14 homework?
Yeah.
Yeah.
It was due from the I'm still.
All right, okay, thank you.
It was there. There was a due date for it.
And I did it, so here we go.
Beck, I wish you could see my eyes rolling back into my head right now.
I can feel it all the way down in Green Bank, let you know.
Good. I like that.
Oh. I'm good.
Okay. So this is not the exact title of chapter 17, but it's the gist of what's going on. Chapter 17 is all about carboxylic acids and the things that we can make from carboxylic acids, or at least some of them. So derivative means it is derived from, all right? In other words, these are things that are made from, that are similar to carboxylic acids. So first of all, a carboxylic acid, we all know what that functional group looks like, and we'll have to demonstrate that tomorrow. Has some sort of carbon or hydrogen, it can be also, but the key is that we have a carbonyl group and also an OH group bound at the same carbon. That's what makes a carboxylic acid. All right. So what do we know about carboxylic acids in terms of their properties? First of all, the fact that the OH group exists in that functional group tells us that this type of functional group is likely to make a molecule very, very polar. All right, so small carboxylic acids are very, very polar. If we have a huge R group over here, it can be less polar. They are capable of hydrogen bonding intermolecular forces, because any molecule that has a hydrogen that's covalently bound to oxygen or nitrogen or fluorine is capable of doing hydrogen bonding as its strongest type of intermolecular forces. We won't spend very long on this, but you should remember what the shape around that carbon is in a carboxylic acid. and what the bond angles around that carbon are. What's the shape? Trigonal, planar. All right. Pyramid would be if we had 4 electron groups and 1 out of the 4 was a lone pair. Here we just have 3 bonding electron groups around that central atom. So trigonal planar is the shape and the bond angle's 120 degrees. So carboxylic acids, the most important of their properties is that they are acidic, as you might expect, because they're called carboxylic acids. Now, what does acidic mean? Well, it actually depends on the context. The most common meaning of an acid is that it's something that can give away H+. All right, we call that the Bronsted acid-base definition. All right, something that gives away an H+ is a Bronsted acid. Something that picks up an H+ is a Bronsted base. So what does it look like when a carboxylic acid gives away its H+? I'm drawing in lone pairs here so you can see what's happening here. And what I'm drawing over here on the left with a capital B is just, that's not a boron atom. That is some kind of base, all right? Some sort of base that can take this H+ away from the carboxylic acid. Now, when we do that, this oxygen is left without an H+. So since this thing doesn't have any charge at all, and we've taken an H+ away from it, now the molecule has a -1 charge. And since our base has now picked up an H+, whereas it was a -1 charge before, now it doesn't have a charge. So notice how the charges change over the course of the reaction, all right? Our base goes up by 1 unit of charge because it steals an H+. A plus and a minus together make a neutral. The carboxylic acid was neutral before it lost an H+, so at the end, it is a -1. All right? We call this thing a carboxylic acid. Very often in aqueous solutions or in reactions, we run into carboxylic acids that have lost their proton. So common. And honestly, in aqueous solutions, in water-based solutions, we are likelier to find a carboxylic acid without its proton than with its proton. So in a neutral solution, pH 7, carboxylic acids don't have their proton anymore. It's still a carboxylic acid, it's just one that currently doesn't have an H+ attached to it. So to distinguish between those two, we refer to the carboxylic acid that has lost its proton as a carboxylate. All right. So if the carboxylic acid has its proton, it's just a carboxylic acid. When it's lost its proton, we normally refer to it as a carboxylate. It's our code word to let us know that currently that carboxylic acid doesn't have its proton. Naming carboxylic acids, simple. It is. It's like the easiest to name out of all the functional groups. Why? Think about it the same way as we think about aldehydes, all right? Remember, an aldehyde has a carbon-based group on one side of the carbonyl group and a hydrogen on the other. In other words, an aldehyde can only be at the very beginning of a carbon chain. The same thing is true with carboxylic acids. So, for a carboxylic acid without any substituent groups, all we have to do is count the number of carbons in our longest chain that contains the carboxylic acid, and we have to know what suffix we use to put on the end to signify that this thing is a carboxylic acid. So if this was a 1, 2, 3, 4, if this was a 5-carbon chain, but it wasn't a carboxylic acid, we'd call it pentane. All right. So if we use ane for the suffix for alkanes, then we use the suffix anoic acid for a carboxylic acid. So pentane would become pentanoic acid. Automatically, when we have a carboxylic acid, the carboxylic acid carbon is carbon number 1. So if we happen to have substituent groups, we number and name them based on the fact that we know the carboxylic acid carbon is the first carbon in the chain. All right, so give this one a shot. That's right. What is the longest carbon chain containing the carboxylic acid here? How many carbons long is it? 1. So, as a base name, a 1-carbon carboxylic acid would be called what? Methanoic acid. So this is some kind of a methanoic acid with a Christmas decoration, right? A substituent group. What kind of substituent group do we have? Cyclohexane, which as a substituent group would be called cyclohexyl. All right. So I wouldn't take off any points if you said 1 cyclohexyl methanoic acid. But in reality, since there's only 1 carbon in the main chain, you really don't have to even give a locant for that substituent group if you don't want to. So cyclohexyl methanoic acid would be perfectly fine. There are a number of small carboxylic acids that have common names as well. So we just talked about the formal name for a 1-carbon carboxylic acid. This would be methanoic acid. All right. It turns out that the same way that instead of calling a 1-carbon aldehyde methanal, which is the formal name for it, there's also a common name for it. The name that we use even more often than the systematic name is formaldehyde. All right. So the same way that formaldehyde has a common name, a 1-carbon carboxylic acid and also 2-carbon carboxylic acid, they have common names that are used probably even more often than the systematic name. So a 1-carbon carboxylic acid is referred to as formic acid. That comes from a Greek prefix, formos, I think, that talks about ants. Because the first place that we found formic acid ants make lots of it. Interesting. 2-carbon carboxylic acid. What would the systematic name for a 2-carbon carboxylic acid be? Ethanoic acid, good. So this one we often refer to instead as acetic acid. Acetic acid is the stuff that is tangy that's in vinegar. All right. You would think that if acetic acid tasted tangy, formic acid probably would too. They're very similar in structure. In fact, formic acid does taste sort of tangy. And that is one of the reasons why chocolate-covered ants are actually kind of a decent snack. All right, you get the chocolate and then you get like a little burst of tang from the formic acid that the ants make.
No.
No, thank you. All right.
Is that a common snack in your house?
No, but I've tried them. Yeah, they're all right. I would actually eat like I've tried, I think it was Ethiopian food that had like pan-fried grasshoppers in it. Surprisingly good. Like nice nutty flavor, crispy, crunchy texture.
Nutty.
Decent. Yeah, decent, really decent. All right. So I would definitely rather eat a pan full of pan-fried grasshoppers than go hungry. And actually, I'd probably rather eat those than lots of less flavorful dishes that I've had before. Just have to get past the idea of it.
The 1, 2, 3 Thai has different bug dishes.
Oh, really?
Yeah. A lot.
They do.
I don't buy there.
I don't
You,
think they're
you're not
very-
gonna try them?
Huh?
You wouldn't try them?
No, because that's the reason why I don't buy food there, because I see the bugs on the menu and I'm like, what if a bug get no.
Something
No.
else.
I like to,
here, but on the
I
one side,
do non-my Thai. I love
Hexylmethanoic, is it not?
There's no, I don't see no bugs. or
Nope, the longest carbon chain is a 1-carbon chain. So that is the only carbon that is in the main chain right there. Remember, a carbon can only be in a ring or out of a ring. It can't be both. So all 6 of these carbons are part of the cyclohexane ring that are not the main chain.
Okay,
Does that make sense?
yeah.
There's only a 1-carbon chain and
It's
a
like
6-carbon
I started
ring.
Learning too much other stuff and then I just forget everything else.
It's just them little key things that like.
Yeah, or like I.
That's why I give you examples like this over and over and over, where you have to distinguish between
Yeah.
what's part of a ring and what's not part
Like
of a
I'm
ring.
in here and I'm like, okay, I get this, and then I get home and I get on the homework and I'm like there for 30 minutes trying to figure out why I can't count the carbon.
I mean, trust me, like I don't make a lot of notes before class, but I pick my examples very carefully. All right. That is exactly what that example is making you, forcing you to distinguish, right? Which carbons are part of the ring, which carbons are not part of the ring. All right.
Because basically, if you would have counted that as a second carbon, then it wouldn't really have been a ring. Technically, I don't know, just my way of thinking now, I guess.
Okay.
Proceed.
I have to take a quick 2-second look. Just to be sure that I haven't forgotten any of the beginning stuff in the chapter to talk about. Talked about nomenclature, we talked about. So one thing that we haven't focused on that much is how those intermolecular forces impact the physical properties of molecules with these functional groups. So for example, things that hydrogen bond, like water, the strongest kind of intermolecular forces, they tend to have really high melting and boiling points compared to things with weaker intermolecular forces. So carboxylic acids, because they also are hydrogen bonders, if they're of any size, they tend to have pretty high melting and boiling points. All right. So carboxylic acids bigger than a few carbons big tend to be solids at room temperature because they have such strong intermolecular forces. Acetic acid, a 2-carbon carboxylic acid. This stuff is not a solid at room temperature. It's a liquid. All right. And oddly enough, it has very, very similar properties to water in terms of its melting and boiling points. Acetic acid, what temperature does water boil at on the Celsius scale? Come on, you all know that, 100 degrees Celsius, all right? The Celsius scale was literally invented, like indexed to water's melting and boiling points. All right, 0 on the Celsius scale is water freezing, 100 is water boiling. It turns out that acetic acid boils at 101 degrees Celsius. All right, so if we have a solution of water and acetic acid together, i.e. vinegar, when you boil vinegar, you're boiling essentially both the acetic acid and the water at the same time. They're close enough to the same boiling point that they co-boil out together.
What happens when I don't know where the question is, but when I put baking powder and then I spray that vinegar on it?
Yeah.
What happens there? What's the
Okay.
chemical reaction?
So baking powder
Mhm.
is two different things together.
Okay.
All right. The reason you use baking powder is because if you're using baking soda to make bubbles in your bread or something like that,
Mhm.
the reason that it makes bubbles is because when it reacts with acids, it releases carbon dioxide.
Okay.
So that's where the bubbles in bread come from. But what if your recipe doesn't have any acid in it any place? Then you don't get the bubbles from baking soda. So very often people will use baking powder instead, which is a mixture of sodium bicarbonate, baking soda,
Okay.
all right?
Yeah.
And also an acid, tartaric acid, which is a solid. So essentially, like baking powder has all the stuff in it to make the bubbles without any acid being added. But if you're just worried about what happens when sodium bicarbonate reacts with an acid like acetic acid,
Mhm. I use it to clean, that's why I'm asking.
well, this is
Baking
great. This
powder?
is actually an example.
Soda.
I mean, honestly, like putting these two things together and cleaning with it, you're cleaning with salt water at that point. Yeah.
Baking soda and.
Yeah, this is baking soda. That's vinegar. All right.
Mm.
So why would you neutralize your baking soda and try to clean with that? Essentially, I'll show you what the products are at the end of the reaction. All right. Yeah,
And that's the thing though, it's like.
it doesn't
so
work for you.
If there's like a buildup on my stove and I do that, it creates these.
Try and do
bubbles.
the same. Yeah, the bubbles don't do anything. It's
Oh.
literally just you're making carbon dioxide. What's actually happening to allow you to clean that surface is the scrubby from the sodium bicarbonate that's not completely dissolved in the solution.
So just use salt.
Oh.
Or just use like
baking soda.
the baking soda and water together and make a paste and scrub with that. You don't
Try
need,
that.
you don't
Does
need
it
it.
work as like roughening the surface?
Yeah.
Like if you had like a scrubby.
It's a
sponge.
scratchy pad, a chemical scratchy pad.
So then
Right.
why does the internet?
Hold on, hold on, hold on.
Soda and vinegar.
We
with?
can't sidetrack. We have a lot of stuff to do today, but this is an important reaction because this is an example of how carboxylic acids react as acids with sodium bicarbonate, which is actually a base. All right. So the first thing I'm going to do is I'm going to sort of change the formula here a little bit, because anytime we have something like an ionic compound like sodium bicarbonate, when it's dissolved in water, it's actually split apart into its individual ions. So in water, it wouldn't look like NaHCO3. It would look like Na plus aqueous and bicarbonate, HCO3 minus aqueous. All right. So same stuff, but that's what it actually looks like when we dissolve it in water. This Na plus, when it's dissolved in water, it never does anything. All right. Sodium plus ions are essentially completely inert in water. They do nothing. But this bicarbonate ion is a base. So let's think about what happens when our acetic acid loses an H plus and our HCO3 minus gains an H plus. Then our products would look like this. All right. We would have the anion of the carboxylic acid. In other words, this is the carboxylate of acetic acid.
Mhm.
And we would also have H2CO3, which we often refer to as carbonic acid.
Mhm.
Now, the reason why you get bubbles is because as soon as you make H2CO3, it decomposes. Another reaction happens. And from that, you get water and CO2. That's where your bubbles come from in the reaction. So look at what stuff is actually left over in here at the end. You made water, you made CO2 that's leaving, and then you have Na plus and acetate. So sodium acetate is the stuff that's left over in the solution. Sodium acetate doesn't do anything. Yeah, this is
that's
not
the
really a
pasty stuff?
cleaner. What's that?
The Na plus is the pasty stuff that's left, like the stuff, like the particles, pieces.
The pasty stuff is probably you put so much sodium bicarbonate, so much baking soda in that it just doesn't all dissolve.
Yeah,
That's when you get a paste.
I didn't.
I'm telling you that mixing those two reagents together to make
That's
a
nothing.
cleaning product, you're not making a
really
cleaning
thought
product.
it was doing something.
It doesn't do
I'm not gonna lie.
Doesn't do anything.
It cleans the steel, like, really.
Yeah, now next time you do it,
I'm gonna
try
do
just
it.
making a paste with water and
the
baking soda.
I'm gonna
Not
do it.
baking powder, baking soda, all right? Because if you put baking powder into water, you'll get the bubbles all by itself because of the tartaric acid. There's already an acid in baking powder, so it automatically makes the bubbles, all
I
right?
wonder if bakers have to learn chemistry.
They should, because they do some stupid things, all right? If they understood how baking soda worked chemically, then they would know when they have to use baking powder and when they don't. It's actually never a bad idea to use baking powder in baking when you need to make bubbles and things. Even if there's acid from some other source, like the baking soda is in there, all
I
right?
want to get off topic, but I won't ask any more questions.
That's good. Thank you. Appreciate it. Your whole life has been on a lie.
So now let's
Oh,
look at
internet.
some things that look a lot like carboxylic acids, all right? And most of these things are things that we can make from carboxylic acids. So remember, a carboxylic acid is something like this, where we have a carbonyl group and an OH group bound to the same carbon. If we have that carbonyl group, and instead of being bound to an oxygen with a hydrogen attached, it's bound to an oxygen with another kind of alkyl group attached, another carbon-based group. We call this an ester. Esters cannot do hydrogen bonding anymore unless there's some other functional group on them. So we expect them to be less polar and also to have lower melting and boiling points than a carboxylic acid of about the same size. They're still polar because of the very strongly polarized carbon-oxygen double bond. So we would expect them to have dipole-dipole kinds of intermolecular forces. All right, not quite as strong in intermolecular forces as carboxylic acids. Practically speaking, small esters tend to smell really good. Most of those small esters smell like fruity smells. All right. A classic example of that is this ester that we could make from acetic acid. So that ester smells for all the world like banana extract.
You said for all the world.
Like it smells a lot
So
like,
like very close. Okay.
yes. Most of these esters, because it's just one chemical instead of like the right mixture of esters that real fruits make, they smell like a very kind of distilled one-note version of the fruit smell. But they're very pleasant smelling. We will make several of them in one of our labs. And after we make them, you will try with your nose to detect what sort of fruity smell you are smelling from the ester that you made. It's fun. Yeah, it's a fun lab.
Just don't taste it.
I mean, it wouldn't hurt you to taste it. It doesn't really, like, you know that 90% of taste is actually smell, right? People that can't smell well can't taste well.
I
Okay,
definitely
so
saw that
esters,
could be-
esters don't really taste good, but they smell really good. And if they're put in as part of a recipe where there are other things to round it out, they can influence our perception of taste in recipes.
Do they use that to make fake banana extract?
Yes, that's the primary
That
ingredient
was
in
my
banana
question.
extract. Yep.
These math cat.
They're fooling us.
The other one of our functional groups that look a lot like carboxylic acids replace the oxygen that is bound to that carbonyl group with a nitrogen instead. Now, these are a little harder because the other things that are bound to this nitrogen can vary, all right? These other groups, R2 and R3, they could be carbon-based groups, or they could be hydrogens. But all of these kinds of compounds are called, I refer to them as amides. Other chemists with PhDs, I have heard them call these amides. So I don't think you're gonna seem like not the smartest person in the room if you use either of those pronunciations. I prefer amide. Now, based on how many carbons are bound to this nitrogen of the amide, that's how we tell what kind of amide it is. So, for example, the same way that we talked about how many carbons are bound to the carbon that contains an OH group. So because this carbon that contains the OH group is bound to two other carbons, we call this a secondary alcohol. Right? We can use the same kind of reasoning to distinguish between different types of amides. So let's say that we had an amide where our nitrogen was only bound to one carbon, the carbonyl carbon. We would call this a primary amide. What if our nitrogen was bound to two different carbons and a hydrogen? All right, so we would call that a secondary amide. And if our nitrogen was bound to three carbons, a tertiary amide. This gets a little tricky because not all amides end up with the same types of intermolecular forces. When we look at primary and secondary amides, we can see that there are bonds, covalent bonds between nitrogen and hydrogen, which means that primary and secondary amides are capable of doing hydrogen bonding intermolecular forces, the strongest kind. A tertiary amide does not have any hydrogens with a covalent bond to nitrogen, which means that this type of amide could only have dipole-dipole attractions. So when we're talking about reactions of carboxylic acids, one of the main things that we do with carboxylic acids is turn them into esters or into amides. There are lots of ways to do that. I am teaching you like one way to do each of those things, but there are lots of ways. We've already talked about the first reaction of carboxylic acids, which is if we put a base in there with them, the base will take away the H plus from the carboxylic acid. All right. We saw that with sodium bicarbonate in the example that Asacia gave us, but it can be any base. One of the most common, easy bases to use is sodium hydroxide. We know that in water, when we dissolve sodium hydroxide, we get Na plus and the hydroxide ion, OH minus. So OH minus is very, very basic, which means it can steal the H plus away from our carboxylic acid. So if OH minus picks up an H plus, what do we end up with when we put OH minus and H plus together? We end up with water.
Mm.
We are going to get back to color coding our reactions here because it's kind of hard to keep track of where the carbons are coming from. All right. But this is a sort of generalized way that we would make an ester from a carboxylic acid. So I'm drawing my ester right here. And we are going to mix that ester with an alcohol. And I'm showing that alcohol with a different alkyl group attached to it than our alkyl group that was part of the carboxylic acid. So R and R2, we can distinguish between those. And I'm also using colors so that you can see where the carbons are coming from. If we use some sort of an acid catalyst, like H2SO4, we end up getting a reaction where this OH group comes off and gets replaced with this oxygen that's bound to the other alkyl group. Now, think about, for balance's sake, what atoms are left over here. We didn't use that hydrogen from the alcohol, and we haven't shown where this OH goes. What's HOH? Water. Yeah, the other one of our products in this reaction is water. I'm just color coding it so you see where the water comes from. All right. So this hydrogen, actually, it should be the other way around. God darn it. I color coded wrong. All right. So it should be there. The hydrogen from our alcohol and the OH group from our carboxylic acid, those are what come together to make the water in the product. All right, now our color coding is correct. So let's try and look at a couple of specific examples of this. All right, we'll color code the first one, and then after that, we'll stop color coding. Notice also that this kind of reaction is very, very similar looking to the way that we make acetals with aldehydes and ketones. It's the exact same reaction conditions. We treat with some sort of alcohol and an acid catalyst. The difference is what we're starting with. When we start with a carboxylic acid, we only end up using one of those alcohols to combine with it to make the ester. When we're starting with an aldehyde or ketone, we have to use two of those alcohols to end up with our acetal. So make sure that you can identify the difference between those reactions because the reagents themselves are identical. All right. In both cases, we're treating with some sort of alcohol and an acid. I can. Billy, what's your question?
Just the bottom.
You can keep writing. If you're not done writing yet, just write. You don't have to take a picture if you're not holding up the class. If you haven't gotten done writing, then other people probably haven't either. All right. So let's look at an example. This is another carboxylic acid that has a common name. This common name is so common that it's actually used as part of the IUPAC system now. So the same way that toluene is used instead of methylbenzene, benzoic acid is used instead of phenylmethanoic acid. But what we're going to do with this benzoic acid is we are going to treat it with 2-propanol. I promised you color coding. We'll do that. And if we use an acid catalyst, what would our products look like from that reaction? I'm going to give you guys one more example because I am trying to hydrate much more regularly than I have been. My bladder is not dealing well with it. So I gotta go use that.
Isn't that fun? It's like drink a lot of water.
I also don't know if it's like, is it that I'm changing the way that I'm living, or is it that I'm in my mid-40s and my bladder doesn't work as well as it did?
Probably a little bit of both.
I don't know. Yeah. I don't like it though.
It's the water. It comes right back out.
All right. So try those two. I'll be back in just a second.
Do you realize how we will teach you the most simple problem, then gives you the hardest one to try? Like, try this. I just talked to
Forget about all of that.
Hey,
I don't even get none of this at this point. Like I was keeping up right at this point. I feel like I'm just like listening and writing it down
Once I got
because
to like chapter 14, I was like, I don't know what we're doing.
that's literally how I feel. I'm just here.
Yeah.
Agreed.
I'm grabbing onto little information, but I have to solidify it by watching the videos again and doing the homework. And then I'll be like, okay.
Well, good for you, because my brain is out the window.
Got 2 words in.
Well, I was thinking about it like this, the homework and stuff weighs a lot, so if I bomb the first test and then just catch up after, I should be all right. It's killing me. Or like, I had everything down and I was understanding it, and then like you start getting into the more detailed stuff and I start forgetting the simple shit, like how to come to my apartment. It's like, what is going on? I just forgot.
I think it was a snow day. I don't know.
I don't know.
After that, I was lost it.
The very first reactions that we did make sense. The rest of these.
I think it was like, so all of the,
Well, those colors don't look as different on the screen as they do on the page. All right, take in the difference between those colors right now, and then I'll turn the page around and show you what it looks like, even from the back of the room.
Oh, I didn't even know you were roasting red.
Yeah.
I should have got her money. I feel like she knows.
And if you're even partially red-green colorblind, you probably don't like this at all.
Is that red and green?
No, it's red and blue. Well, it's actually like
Looks black and blue.
purple and blue.
It's fine, as long as you don't use, I have troubles with shades. So as long as it's not 2 different shades of blue, I'm golden. But it's like, you put 2 shades of blue together, and if it's not like black and white difference, I'm like, I don't know.
Can't
I'll tell you.
What's that?
Me looking at this, trying to see if I lost it or if I got it. I'll just wait till he does it.
I got that part. Oh, so you, okay. Oh. H from there.
What,
Yes, Becca?
on the benzonic acid, what, how come after that second oxygen,
Okay, I see the H2O.
yeah, well, can you go over what? That,
This
or-
oxygen is this oxygen.
Yep.
Look at what's attached to that oxygen here. A 3-carbon chain connected at carbon 2. The same 3-carbon chain connected at carbon 2 is on that oxygen once it's attached to the carbonyl group.
okay, thank you.
So water is always gonna be a product.
Yes,
And you're combining what's left. You're combining the two.
yes. Generally speaking, reactions like this that produce water as one of the products of the reaction are called condensation reactions. So condensation reactions that produce water, normally the other parts like are two big things that end up together and a water gets lost in the middle. All right. The cool part about this is that these reactions in the exact reverse are the way that we turn esters back into carboxylic acids, because these are equilibrium reactions. So Le Chatelier's principle tells us that if we have too much of a reactant, the reaction will push to make more products. All right. So the way that we make this kind of reaction work is we put a large excess normally of the alcohol here, which pushes the reaction to turn all of our carboxylic acid into the ester. But what if we already had the ester and we wanted to break it back apart into the carboxylic acid and the alcohol? The way we would do that is by adding a large excess of water instead. And then we would add our acid catalyst. So these reactions are equilibrium reactions. We can do them in the forward direction to make the ester, or if we add a lot of water instead to the ester, we can do the reverse reaction and turn the ester back into the carboxylic acid part and the alcohol part. So the opposite reaction where we're using water to split the two pieces apart, those are called hydrolysis reactions. Hydro, water, lysis, cutting. All right. We're using water to split that ester back apart. I hate even teaching you this version of this reaction, but so now we know how to make esters from carboxylic acids. How do we make an amide from a carboxylic acid? In real life, there are lots of ways that chemists do this. Almost no chemists use the way that you're learning in this book to do it. The reason why we're teaching you this way is because it's easy to look at. Most of the time, when we turn a carboxylic acid into an amide, we normally do it over a couple of steps. As a matter of fact, it would probably be much more common, instead of starting with a carboxylic acid to make an amide, we might start with an ester and turn that into an amide instead. All right, but lots of steps and thinking about mechanisms are not things that are fair for a non-majors class to worry about. So we're doing a reaction that works. It's just like, nobody really does it this way in real life. So by putting a carboxylic acid together with, by the way, this is called an amine, if it's a nitrogen with one or more alkyl groups attached to it. If there were no alkyl groups attached, it would just be ammonia, NH3. Putting those two together with heat will allow us to do another condensation reaction. So look carefully at where the water comes from here. That OH group ends up leaving. Also, this hydrogen attached to the nitrogen ends up leaving. That's where our water comes from. So treating a carboxylic acid with an amine, if we heat the two of them together, even though in real life we don't normally do it like this, all right, this is one way that we could make an amide. Let's look at a real example now instead of a one with like lots of R's. If we started with acetic acid, and we treated acetic acid with ammonia, NH3, and then heated in a closed container so that nothing could escape as a gas. You see where the water comes from? That OH group leaves the carboxylic acid. One of the hydrogens leaves the amine as it becomes an amide. And that's where our condensation is occurring. Let's try a slightly more complex one. Yeah, that's a cyclic amine. They're pretty common. I think that one's called piperidine, if I remember right. That's a common for that. Give you enough time to make your best guess, finish making it. Yeah, you got it?
Yeah.
Good. What kind of amide is that? Is it a primary amide, a secondary amide, or a tertiary amide?
Tertiary?
Tertiary, because the nitrogen has 3 bonds to carbons. All right. So I have now taught you how to make esters and amides. This is not the real way chemists make amides, but in reality, there are like, honest to God, like 50 different ways that chemists turn carboxylic acids into amides. It's a really, really important reaction because the key bonds in one of our most important biological molecules, proteins, the key bonds are amide bonds. So taking amino acids and linking them together to make a protein, we are making amides at each one of those connections between our amino acids. So chemists have to know how to do that and do it really well. All right. They got lots and lots of ways to do that. So now we're looking at the reverse reaction of the esterification reaction that we just looked at. So when we turn a carboxylic acid into an ester, we use the fancy name esterification. We are esterifying our carboxylic acid. All right, this is breaking the ester back apart into the carboxylic acid and the alcohol. All right, and we do that with water, so it's a hydrolysis reaction. So in general, it looks like this. What's really interesting, though, is that the same way that we can use an acid catalyst for esterification, we can also use it for hydrolysis. So when we split those two parts back apart, we end up with our carboxylic acid back, and we end up with our alcohol back. The crazy thing is that because of how esters work, we could also use a base instead of an acid to do this hydrolysis. As a matter of fact, when we did hydrolysis of esters in lab, which we did already, all right, do you remember where we did it? This is the reaction that we used to make soap. We took esters in a triglyceride and we split them apart to make carboxylates. Those were our soap molecules. And then glycerol. We did that with NaOH. So this is confusing to a lot of students, but think about what products you're making, all right? Anytime we split apart an ester, we're going to get back our carboxylic acid and our alcohol. Always. But when we do this under basic conditions, the products just look a little different. Because we know that in basic conditions, carboxylic acids lose their protons. So because the base is around, our carboxylic acid doesn't have its H plus anymore when we get it back. So when you're starting to learn about these hydrolysis reactions, remember that whenever we hydrolyze an ester, we're getting back our carboxylic acid and our alcohol. It just looks a little different depending on how we do the hydrolysis. All right. In acidic conditions, there are plenty of H pluses around so that our carboxylic acid has its H plus attached. In basic conditions, we know that carboxylic acids lose their H pluses. So that's why this carboxylic acid doesn't have one anymore, because of the base. We can also split apart an amide. And we can split apart an amide using acid or base, the same way that we can do that with carboxylic acids. Or sorry, with esters. So how did we make an amide? We made it by putting together an amine and a carboxylic acid. So when we split that amide apart, what are we going to get back? An amine and a carboxylic acid. Now, when we do this reaction using acid as the catalyst to do the reaction, we know that in acidic conditions, our carboxylic acid is going to have its H+ attached. Here's the kind of crazy thing that happens to amines, though. The same way that carboxylic acids can lose an H+ in basic conditions, amines can gain an extra H+ in acidic conditions. If we did the same reaction, the same hydrolysis using base like sodium hydroxide, we know that when we get a carboxylic acid in a basic solution, that carboxylic acid is going to have lost its proton. And in a basic solution, our amine would not have picked up an extra proton. So in both of these cases, we end up with some version of the carboxylic acid and the amine as products. But what those two products look like depends on whether we're in an acidic solution or in a basic solution. All right, with carboxylic acids, it's easy. In acidic solutions, they have their H+. In basic solutions, they don't have their H+. We have a similar thing with amines, though. In acidic solutions, amines, they end up picking up one more H+ than they normally would. In basic solutions, they don't. So let's look at some real examples that don't have any R's in them of each of these now. So if we did hydrolysis of this ester in acid, what would the products look like? And what about if we did the same reaction in basic conditions instead? Remember when we split apart our ester, we always get a carboxylic acid and an alcohol back. All right, regardless of how we do it. We just have to be careful to write those two products in the way that they would look in acidic conditions and in the way they would look in basic conditions. All right. So in acidic conditions, we know that our carboxylic acid part is going to have the H attached.
Does it matter where you put the OH?
You tell me.
Long, if, is it, if it, as long as it's connected to one of those double bonds, is it okay?
In what?
I mean, for where you have to put the OH, I also had that same question, and then,
It's not connected to a double bond, it's connected to a carbon. And all 6 of those carbons have what looks like a carbon-carbon double bond attached to them, right?
Yeah.
I was hoping that you guys would be comfortable enough at this point to realize that that and that are the same things. I did it on purpose. Now, in basic conditions, carboxylic acids, God, I just drew it wrong, right as I was saying what it did. In basic conditions, carboxylic acids lose their H+. And we still get our alcohol back. I'm telling a little white lie here because it's sort of not that germane to the reaction that we're looking at right now. But for reasons that we don't have to talk about in here, this hydrogen would actually also be lost to the base. Normally, alcohols don't lose their H pluses in sodium hydroxide. All right, this one is a really special H plus. It's more acidic than your normal ones. I just don't want to go through the can of worms to explain why that is. Okay, so I'm drawing it, and I'm also telling you that there's a little white lie in this molecule right here that we don't have to worry about for right now. All right, I just don't like lying to you and not at least telling you that I'm lying to you.
It's okay, like to
Yeah.
us.
I doubt that in my lifetime I would ever be like, you know, this molecule right here, this is right, and somebody's gonna say, that's wrong, somebody lied to you.
You never know. So that OH group, an alcohol that's attached to a benzene ring, is about 10,000 times more acidic than an alcohol that's not attached to a benzene ring. All right. We don't have to understand why that is. It's really cool. All right. We don't have to understand why that is for this class.
You're pushing me to wanna know why now.
Well, that's why you gotta take majors level organic chemistry, because then all the whys are uncovered. It's so much fun. It
Even if I don't
really
understand
is
it.
fun. If you have a good professor that gets to the why instead of just buries you in the what. In other words, instead of just giving you 1,000 different examples of chemical reactions, if they focus on why they happen the way they do, organic chemistry is the awesomest thing ever. That's my humble opinion. Again, I did organic chemistry in grad school, so obviously I'm gonna like it at least a little bit. Either that, or maybe just I'm really stubborn and I managed to hate it and still get a PhD in it after 5.5 years. That'd be an awful way to live. Yeah. Willingly doing something that you despise for 5.5 years for an end goal of a job.
I'm
Gross.
doing that right now. Locked in a contract.
Gross.
Guess what, I despise it and I'm still about to go realist.
You read this thing?
Probably as a reservist. Same thing, we still got you, they can be like, 2 years, back to active duty, sis.
Now we're gonna look at hydrolysis of an amide. What does that look like? What do those products look like in acidic conditions? What do they look like in basic conditions? Yes, I drew my amide backwards this time. The N is on the left instead of on the right. I did it on purpose. We want our knowledge to be robust, not confined to one small particular way of knowing.
Thought I was stressing about the first test, I haven't even done it yet, and I'm stressing about the second test.
We got a long time, at least like another couple of weeks after this week before the second test happens.
Sure.
Make your flashcards. When you make a flashcard for ester hydrolysis, make that 2 flashcards. What do the products of an ester hydrolysis look like in acid? What do the products of an ester hydrolysis look like in base?
I feel like you can make a lot of money.
Yeah, but it means more if you make your own flashcards, right? Your own style.
Right.
Could I sell a set of flashcards for this class? Yes.
Yes.
But like, it's just, the help is just as much in making the flashcards as in using them, right? If I just give you the flashcards and you look through them, like, that's the same as if I give you a practice test and I give you an answer key for it. Students are gonna look at the answer key and be like, yep, I would have guessed that. And then they get to the real test and they get them all wrong because they're not actually thinking about the questions.
I feel like I know the answer to this question, but I'm gonna ask it anyway. The test is not multiple choice, huh?
Some of it is, actually a lot. Have you looked at the practice exam?
Yes, I did.
There were multiple choice questions on it, weren't there?
But
Okay.
I wasn't sure.
So you're like, you're saying that I'm going to be intentionally deceptive and change the format of the test?
Precisely.
Maybe.
I could change the format of given questions, all right? So
Not unrealistic for,
you should be prepared for the same kinds of questions to appear in any one of a number of formats.
They do that in nursing school.
yeah, that's what I'm saying, like. you
Study
just
for
go in-
everything and then you show us.
It's totally
what the
different.
fuck.
Like, and two, sometimes like having a option of choices versus like physically having to only give this one answer, does that make sense?
Yep.
Is like,
I find fill-ins easier than multiple choice because multiple choice answers can be intentionally deceptive. And a fill-in, like you either know it or you don't. You can't get fooled by the choices.
but at
Depends
least
if
you
you're
have a
somebody
choice.
who's good at elimination. I am very good.
I am testing whether people are good at chemistry, not whether they're good at taking a multiple choice test. All right. In acidic conditions, our carboxylic acid will have its proton. I drew it on the right because the carboxylic acid part is on the right of this molecule. In acidic conditions, amines pick up one more proton than they normally would. So that nitrogen will end up with a plus charge and 3 hydrogens attached. That is one more hydrogen than that nitrogen would normally have on it if it wasn't in acidic conditions. Notice that maybe it would help for me to talk to you about, in a neutral solution, all right, a neutral or basic solution, an amine normally has a pair of electrons and then 3 bonds to other things. In acidic solutions, because amines are bases, in other words, because they can pick up protons, amines end up with 4 bonds to nitrogen and a plus charge in acidic solutions. So, how are our products going to look different in basic conditions? In basic conditions, a carboxylic acid will not have its proton. It will be a carboxylate. Our amine in basic conditions would be neutral instead of plus charge. And as a matter of fact, we have a naming convention for amines the same way we do for carboxylic acids. So when carboxylic acids have lost their protons, we call them carboxylates, all right? When amines have gained a proton, we call them ammonium ions instead. Wow, we freaking killed it. All right, it is an hour and a half into class. We've literally covered all of chapter 17 at this point. Does that mean we will not practice these reactions any longer?
No.
No, of course not. All right. So tonight, do I expect you to go home and spend 2 hours pining and thinking about chapter 17 when there's an exam tomorrow?
No.
Probably not. All right. Spend your time making sure you're ready for exam 1, 11 through 14. But over the weekend, spend some time with chapter 17, look at the examples, do some homework problems, and look at the answers for the odd numbered exercises that the answers are there in the back of the book. All right, see if you can make sense of this set of reactions.
I think my light bulbs go off. The best time of night is at 11:30, 12 o'clock.
That's when you're at your peak for doing homework.
Yeah, like I literally am sitting there looking at everything and then randomly sometimes.
Yeah, know that about
Sometimes
yourself.
light
All of
bulb
us are
just goes
different.
off.
All of us are different.
Morning.
All right. I'm weird. Sometimes like I have to like find a wave, and it's not always at the same time. Sometimes if I get up really early, I'll have like after I have a cup of coffee and sit there for a minute, I'm like, okay, it's time to learn, or okay, it's time to grade right now. I'm gonna kill it, right? Or sometimes
I have those.
like I'm
days.
relaxing on the couch after dinner and it's like 9 o'clock at night and I'm like, okay, time to kill it right now, right? So you just have to find out like when your best time to learn is and use that.
When I wake up
Yeah.
before everyone in the house and have a cup of coffee, complete silence.
You like-
Oh, isn't that nice? You wanna borrow my computer?
Huh?
You wanna borrow my?
All right,
computer?
that's all for us today. Study hard. Remember, we have our exam, so we have to be here in the room tomorrow to take the exam. Nobody has said anything about not being able to make it in person, so I'm hoping to see every one of you tomorrow. And have a wonderful afternoon.